Подождите, я правильно помню, что Маш ни тебя Влад не было в прошлый раз?
Я был.
А, ты был.
Я просто всегда
Я
чуть
вроде
пораньше
ж была.
ухожу, но вообще я был.
Я вроде была. Может, я, конечно, что-то порубал, но вроде нет.
Проверь. Все правильно? Все, в эфире.
The previous lecture we discussed the limits of locally convex spaces. So let's briefly recall the definition. So we have a category A, an arbitrary category, a small category I, and a covariant functor f from I to A. A typical example to keep in mind is the case where I is a partially ordered set. We can make it into a category as follows. If, say, you have two elements I and j, and I is less than or equal to j, then there is a unique morphism from I to j. And if they are not comparable, then the set of morphisms is empty. And the composition law is defined in the only possible way. The limit, we define the limit of f is, first of all, it's an object, denoted like this. And second, a natural isomorphism between the home functor from y to the limit of f, and the home functor from delta y to f, where delta y is the constant functor. So let's recall that delta y is defined as follows. It takes every object to y, and it takes every morphism to the identity morphism of y. So this set of morphisms is considered, so these are morphisms in the category A, and these are natural transformations. So they are morphisms in the category of functors. From I to A. Let's denote this category like this. The same definition can be made a little bit more explicit if we recall that the elements of the set, so let me write this down explicitly, remark. So the elements of the set, morphisms from delta y to f, are cones over f with vertex y. So let's recall that a cone over f is the following picture. This is y, and for every arrow from I to j in the category I, we get an arrow here, and we should have a family of morphisms from I to every object f of I, such that each such diagram is commutative for every arrow alpha from I to j. It's more or less clear how to define morphisms between cones. So you have two cones with vertices, say, x and y, then a morphism from the first cone to the second one is just a morphism from x to y, such that all the respective diagrams are commutative. And from this point of view, the limit of f, the limit f is nothing but the terminal object. Terminal object in the category of cones over f. Okay, so this is the general definition. It makes sense in any category. So again, I don't claim that such a limit always exists. Sometimes it exists, sometimes it doesn't exist. But anyway, this definition makes sense for any category. And now let's recall how it looks like in concrete cases. Limits in the category of sets. So now A is the category of sets. I claim that in this case, every functor from any small category to the category of sets has a limit. It can be, this limit can be explicitly described as follows. It's actually a subset of the product. It consists of all elements xi in the product of the sets f of I. Such that for every arrow alpha in our category I, the element xj equals f of alpha applied to xi.
But it usually will be empty set.
That depends on the that depends on the functor.
Of course.
In our concrete situations, it will be not empty. But if we know nothing about f, then in general, yes, it can be empty. Okay, so this is a subset of the product, and the respective. So to define a limit, so let's recall that the limit is a cone. So we should also explain the canonical maps from x to the respective f of I. They are just restrictions of the projections. So phi I from x to f of I is just the restriction of the canonical projection of the product onto the respective onto the respective object, onto the respective set. So it can easily check that x together with this. Let's make it a bit more. So x together with this family of maps is the limit. So this is the limit in the category of sets. And of course we are mostly interested in limits in the category of locally convex spaces. Limits in the category of locally convex spaces. And again, I claim that here every functor has a limit. And it is explicitly constructed as follows. We simply take the limit in the category of sets. So A is the category of locally convex spaces. And if we have a functor with values in this category, we let x denote the limit of f. The limit of f taken in the category of sets. And we observe that x is not just a subset in the product, it's actually a vector subspace. X is a vector subspace of the product. And we equip it with the topology induced from the product. Equip x with the topology induced from the product. Or equivalently with the projective locally convex topology generated by the family of all canonical projections. And in this case, I claim that X together with the same family of maps phi I is the limit of F in the category of locally convex spaces. So this is an explicit characterization of limits. An important special case, which I've already mentioned at the beginning of the lecture, is the case where I is a pose set. Special case. Suppose that I is a pose set, and we assume that it is directed. A directed pose set. Directed partially ordered set. And we define a projective system or an inverse system. Inverse system in A indexed by I. To be a functor, a covariant functor, but not from I. This is functor from the opposite category of I to A. So explicitly, this can be described as follows. This is a family of objects, xi, indexed by I. This is a family of objects. Together with a family of morphisms, phi ij, which act from xj to xi for every pair of indices I and j such that I is less than or equal to j. So I'd like to stress that it acts from xj to xi and not the other way around, because f acts from the opposite category. A family of morphisms such that they are compatible in the following sense. Phi ik is just the composition of phi ij and phi jk. If I is less than or equal to j, and j is less than or equal to k. And phi I is, of course, the identity morphism. So in this case, the limit of f, if it exists, is called the projective limit. Or the inverse limit. Of this sequence. And usually it is denoted like this, or we just suppress the notation for f and write just the limit of the respective spaces of the respective objects xi. Of course, there is we should always remember that this notation is not very good, because everything depends not only on the objects xi, but also on the morphisms phi ij. But nevertheless, it's a rather common notation. And in a more special case, is a case where I is just a set of natural numbers. Special case. Suppose that I is a set of natural numbers equipped with the usual order. In this case, a projective system is simply a projective sequence. A projective sequence that is a diagram of the following form: x1, x2, x3, and so on. This is 5, 1, 2, 5, 2, 3, 5, 3, 4, and so on. at first glance, to define a projective system indexed by natural numbers, we should also define phi ij for every pair of indices, such that I is less than or equal to j. But it's clear that because of this rule, there is only a way to define phi ij. So phi ij will be simply phi I plus 1, phi I plus 1, I plus 2, and so on, phi j minus 1, j, for every I less than or equal to j. So to define a projective sequence, it's indeed enough to define the maps from the morphisms from x n plus 1 to xn for every. So if we now look again at the general definition of a limit, so the terminal object in the category of cones, so we can write the following picture once again. So a projective limit of a projective system is an object of our category together with a family of morphisms from here to here. So for all the objects xi, this is phi I, this is phi j, such that this diagram commutes whenever I is less than or equal to j, and such that for any other object I and any other compatible family of morphisms, that is a family of morphisms psi I from y to xi, such that again for every pair of indices I and j, such that I is less than or equal to j, this diagram commutes. So for any such y, there is a unique morphism from here to here, which makes the diagram commute. So this picture illustrates the definition of projective limit. Okay, let's now look at some examples. We have already discussed some of them at the end of the previous lecture, but for completeness, I'll repeat them and I'll give you some more examples. Example 1. So we'll consider the following situation. Suppose that we start with a locally convex space X. X is an arbitrary locally convex space. And suppose that we have a chain of subspaces, a decreasing chain of vector subspaces. And of course, we can look at it as a projective sequence. So the respective errors are just the inclusion maps. And it's more or less clear that the limit, projective limit of this sequence, is nothing but the intersection of these subspaces equipped with the subspace topology. Why is it so? By the way, in all such situations, in all such concrete situations, to prove that, if you want to prove that the projective limit is isomorphic to something concrete, it is not very convenient to use this concrete description of the projective limit. Instead of this, it is much more convenient to check the universal property. I don't claim that this approach doesn't work. Of course, if you like, you can always consider the product and then explicitly construct an isomorphism between the respective subspace of the product and the second space. But in my view, it's much more natural and it is much easier to check the universal property. Well, indeed, what is a cone over this chain? Well, a cone over this chain is a compatible family of maps from Y to all these spaces. It's clear that to give such a compatible family of maps is the same thing as to give a continuous map to the intersection. And that's it. So this implies that the projective limit is just the intersection. Example 2. Example 2, consider the following projective sequence of finite dimensional spaces K, K2, K3, and so on. So the connecting maps are just the projections. x1, x2 goes to x1, x1, x2, x3 goes to x1, x2, and so on. So this is a projective sequence, and I claim that the limit of this sequence, projective limit of this sequence, is the space of all k-value sequences equipped with the product topology. And again, why is it so? Again, we look at cones over this sequence, and we easily observe that to give a map from to give a cone, to give a compatible family of maps from Y to this chain is the same as to give a map from Y to the product. And the continuity of the respective map is equivalent to the continuity of all the coordinates. So this is indeed the product topology. So we see that this product satisfies the respective universal property, so it is indeed the limit of this projective sequence. In fact, so we see that in this example, an infinite product, a countable product, is interpreted as a projective limit of finite products. And in fact, this phenomenon can be generalized as follows. Example 3. I'm trying to make the pen on the left blackboard identical to the pen on the right blackboard. Example 3. Suppose that we have an arbitrary set I and an arbitrary family of locally convex spaces xi. A family of locally convex spaces. Let's consider the set whose elements are arbitrary finite subsets of I. And we denote it like this. It's the set of all finite subsets of I. And clearly this is a directed poset. So the order relation is just the inclusion. It is directed because the union of two finite sets is finite. Now for any finite subset of I, for A and J, let xj denote the product of those spaces xi where I runs over j. So this is a finite product of our spaces. If now we have two finite subsets, k and j, where k is contained in j, then we have the projection from xj to xk. So we see that the spaces xj form a projective system indexed by thing of I. And I claim, this is a little exercise, that the limit of this projective system, xj, where j runs over the finite subsets of I, is nothing but the product of all our families. This is a natural generalization of example 2. So every product can be reduced to the projective limit of finite products. Okay, example 4. Example 4. Consider the following projective sequence. So for every n, we consider the closed interval from minus n to n. And here we have the restriction maps. Restriction maps. Of course, we equip each space of continuous functions with the supremum norm, so it's a Banach space. I claim that the limit of this projective sequence is nothing but the space of continuous functions on the real line together with the compact open topology. This is a little exercise, but let me just explain why it is so. Formally, to prove that such an isomorphism exists, we first of all we should make C of R into a cone over the minor spaces of continuous functions on the intervals, and it's more or less clear how to do it. We just take the restriction maps, and they are compatible in the obvious sense. So this becomes a cone over these spaces. And even now I have another cone. Well, maybe this is not a good picture. I'm sorry, I should move it to the left a little bit. So this is the restriction map. And if we have another locally convex space Y, together with a compatible family of maps from Y to the spaces of continuous functions. So we must show that there is a unique map from here to here, let's say chi, which makes the diagram commute. So let's know this by phi n. So to define chi, we should define chi of y for every element little y. So this should be a function of the real line. So to define this function, we must explain what is the value of this function at every point little t. And to define this, we simply find n in such a way that t belongs to the interval from minus n to n. And for every such t, we let this, so this will be phi n of y evaluated at t, if t belongs to this interval. And now to complete the proof, we must prove that this is, first of all, this is well defined. This doesn't depend on n. If we replace here n by n plus 1, then we get the same number. And also we must show that this chi is continuous and it is a unique map making this diagram commute. But this is more or less straightforward. Again, this example can be generalized to a more or less arbitrary topological space. Example 5. Suppose that X is a locally compact topological space. Again, this assumption that X is locally compact can be weakened, but I don't want to discuss some delicate points from general topology. Anyway, if X is locally compact, then this example works. So I claim, this is a little exercise, prove that C of X, the space of continuous functions on X, is isomorphic to the projective limit of spaces, or the spaces C of K, where K runs over the collection of all compact subsets of X. To make sense, to give a meaning to this expression, I must explain the connector maps and to introduce the respective power set. Well, the power set is clear from the context. This is the set of all compact subsets of X, ordered by inclusion. And the connector maps are just restriction maps, just like in example 4. And I claim that we have this isomorphism. And one special case is the case where X is second countable. So if X is not only locally compact but is also second countable, which means that it has a countable base. The topology on X has a countable base. Then it's rather easy to construct so-called compact exhaustion of X. exists a compact exhaustion of X, that is a family, a sequence of compact sets, say Kj, of compact subsets of X, such that X is the union of the sequence, and Kj, every Kj is contained in the interior of Kj plus 1 for every J. This is also part of the exercise, but just a simple exercise from general topology. And if we choose such an exhaustion, so in this case, we can represent C of X as a countable projective limit of the spaces C of Kj.
Can you repeat please an example for we have some negative results?
No.
Там стрелка зачеркнута. Это хи.
This is chi, sorry. I claim this chi exists and is unique. This is a direct generalization of example 4. Here we have a countable projective limit, and a special case is the case where x is the real line, and kj is the interval from minus j to j. Okay, example 6 is similar to example 4, but now we, by the way, before we discuss example 5, let's observe that, for example 6, let's observe that in all these examples, in example 4 and in example 5, our space of continuous functions is represented as a projective limit of Banach spaces. So this is a Banach space. Example 6. It looks similar to example 4, but now we consider the spaces of ck functions. C1 on from minus 1 to 1, C2 from minus 2 to 2, and so on. All of them are Banach spaces with respect to their canonical norms. So what are the errors? Well, they are more or less clear. We simply restrict every ck plus 1 function to a smaller interval and consider it as a ck function on a smaller interval. So these are just the restriction maps. So what is the projective limit? This little exercise proves that the projective limit of the sequence is nothing but the space of C infinity functions on the real line. So the proof is more or less the same as in the case of continuous functions. And again, we see that the space of smooth functions on the line is isomorphic to the projective limit of Banach spaces. By the way, useful exercise is to generalize this example to the space of smooth functions on an arbitrary manifold. And to show that C infinity of M can also be represented as the projective limit of Banach spaces. Example 7. First of all, we introduce some notation. If K is a compact subset of Cn, then we may consider the space A of K, which consists of those continuous functions on K, which are holomorphic on the interior of K. Well, this is a closed vector subspace of C of K, and so it's a Banach space. We can now use such spaces to represent the space of holomorphic functions on an arbitrary open subset of Cn as a projective limit of Banach spaces. So, more exactly, you take now an open set U in Cn, and we choose a compact exhaustion, Kj, a compact exhaustion of U, and again, it's a little exercise to prove that the space of holomorphic functions on U, and the canonical topology of the space is just the compact open topology, this space is isomorphic to the projective limit of the Banach spaces A of Kj. The connecting map again are just restriction maps. So if I have a function on Kj plus 1, we simply restrict it to Kj. And we see again that this is projective limit of Banach spaces. Okay, example 8. Example 8. Consider the following projective sequence: L infinity, again L infinity, again L infinity, and so on. And what are the connected maps? Again, we have the same connected map everywhere, phi, which acts by the following formula. This is just the diagonal operator. It takes a bounded sequence x1, x2, and so on, to the sequence x1, x2 over 2, x3 over 3, and so on. An exercise. First of all, the projective limit of this sequence is nothing but the space level S of rapidly decreasing sequences. So there is a topological isomorphism between this projective limit and little s. And second, actually we can replace here L infinity by LP. L infinity can be replaced by LP, where P is an arbitrary number between 1 and infinity, or by little c0, the space of the Banach space of sequences which vanish at infinity. And the result will be the same. So the projective limit will be isomorphic to little s. Okay, so by looking at this example, these examples, we see that that projective limits are everywhere. So many concrete locally convex spaces can be represented as projective limits of Banach spaces. And we will see soon that this is not a coincidence. Actually, we will prove maybe at the next lecture that every complete locally convex space can be represented as a projective limit of Banach spaces, which is quite useful. Okay, let's now discuss the dual notion, namely the notion of a co-limit. Again, we start with an abstract definition. So suppose that we have a small category I, small category, an arbitrary category A, and a covariant functor f from I to A. We define the co-limit of f to be the limit. Co-limit f is the limit of the same functor considered as a functor between the opposite categories. It's still a covariant functor, so by definition, the limit of this functor is the co-limit of f. So explicitly, this can be written as follows. the co-limit of f is an object denoted like this. And a natural isomorphism between the morphisms from the co-limit to y and morphisms, or more exactly natural transformations, from f to the constant functor delta y. So these are morphisms in A, and here we have natural transformations, that is, morphisms in the category of functors. Well, this is not a surprise actually, because if you look at the respective definition of a limit, we see that this is just the same, but we simply reverse the arrows here. Also, if we want to make this more explicit, let's observe that the elements of the set which is in the right-hand side of this formula, natural transformations from f to the constant functor delta y, are the cones over f with vertex y. That is commutative diagrams of the following form. So for every I, we have a morphism from f of I to y, I, and all such diagrams must be commutative for every morphism alpha from I to j. So the only difference between a cone and a cone is in the direction of these arrows. So in the definition of a cone, we had arrows from y to f of I, and here we have arrows from f of I to y. That's the only difference. So if we now look at this interpretation of the set, then we can easily deduce that the co-limit of f is the initial object in the category of all co-limits over f. In particular, this observation shows that if a co-limit exists, then it is unique in the ordinary sense, because the initial object in any category is unique. Okay, so again, let's now give a concrete description of co-limit in the category of, first of all, the category of vector spaces, and then in the category of locally complex spaces. And by the way, final remark which works in an abstract category, a little exercise, is to show that co-products are special cases of co-limits, similar to products. So in the previous lecture we have seen that product is a special case of a limit. And in the same way, a co-product is a special case of a co-limit. And also co-kernels. Co-kernels are special cases of co-limits. Okay, so let's now look at the category of vector spaces. Again, a rather straightforward exercise. So suppose that A is the category of vector spaces. F is still a covariant functor. And let's construct the following space, we denote it by X. First of all, we take the co-product, the direct sum of the spaces f of I. And then we take the quotient out the linear span of all elements of the following form, x minus f of alpha x, where x runs over f of I, and alpha runs over all arrows from I to j. So this sits in the ith summand, this sits in the jth summand. So we simply identify these two elements of the direct sum. If they are connected by an arrow, then we simply identify them. This is, of course, this is x, not alpha, this is x. So this is our space X, and so if we want to prove to show that X is a candidate for the co-limit, we must also construct maps from f of I to X, because X should be co-co. Well, this is quite easy. So for every I we have, well, let's denote it by j. For every j we have the canonical inclusion of f of j into the direct sum, f of I. And here we have just the quotient map onto X. So we compose these two arrows and we get a map from here to here, denoted by phi j. And I claim, this is an exercise, that if we consider this space X together with this family of maps phi I, then we get the co-limit of f in the category of vector spaces. Okay, so this is the first part of the exercise. And now let's conduct analysis and consider the category of locally convex spaces. And again, just like in the case of products, here the situation is similar to the category of vector spaces. So if you have a functor with values in the category of locally convex spaces, then we can easily consider this functor as a functor with values in the category of vector spaces. And we let X denote the co-limit of f in the category of vector spaces. So we look at the space, and we recall that we have already defined a canonical topology on the direct sum, namely the co-product topology, or the topology of locally convex direct sum. And we already know what a quotient is, in the topological sense. So we equip X with the quotient topology, and the quotient topology. And I claim, this is an exercise, that what we get is nothing but co-limit of f in the category of locally convex spaces. So in summary, we see that every functor from any small category to the category of locally convex spaces has a co-limit, and this co-limit can be explicitly described as the following quotient. Again, in the case of limits, we consider an important special case where I is the category I comes from poset, and the same situation happens with co-limits. So an important special case comes from the following definition. If I is a directed poset, then an inductive system, or a direct system A is a covariant functor f from I to A. So the difference between inductive systems and projective systems is that in the case of projective systems, f acted from the opposite category of I to A. And here we act between I and A. That's the difference. Explicitly, a direct system is the following data. We have a family of objects, xi, and a family of morphisms, phi ij, which act from xi to xj for each pair of indices where I is less or equal to j. Such that they satisfy the following compatibility relation. Whenever I is less than or equal to j and j is less than or equal to k. So again, if we compare this with our definition, our explicit definition of a projective system, we see that the difference is that here, it's not here, sorry. Oh well, let's just look here. So the only difference there is that in the definition of a projective system, phi ij acted from xj to xi. And in inductive systems, it acts from xi to xj. That's the difference. And now the co-limit of this functor f, if it exists, is called the inductive limit. The inductive limit, or the direct limit. And we use the following notation. So the co-limit of f is abbreviated as the limit, but the arrow now acts from left to right. And again, we often write just the limit of xi, assuming that phi ij are already given, but we don't put them into our notation. Okay. And again, just like in the case of in projective systems, an important special subcase is the case of inductive sequences. A very special case. In the case of inductive sequences. That is diagrams of the following for x1, x2, x3, and so on. So they correspond to a case where the index set I. What's that? This corresponds to the case where the index set I is just a set of natural numbers. Again, it's enough to define phi 1, 2. Phi 2, 3, and so on, because for arbitrary ij, we define phi ij to be the following composition. So in summary, we have the following picture, which reflects all the ingredients of our definition. So first of all, we have a family of morphisms, I, ij, defined for all indices I and j, such that I is less than or equal to j. then the inductive limit of xi is an object together with a family of morphisms which act from xi to our object, phi I and phi j. So this shows that our object is a co-clone over our family. And for any other co-clone, that is for any other object y, and any other family of morphisms psi I from xi to y, such that all these diagrams commute, there is a unique morphism from the inductive limit to y, such that this diagram is commuted. So this picture is precisely the dual of this one. So see, we simply reverse all the arrows and we get the definition of inductive limit. Okay, let's now look at concrete examples. Well, before looking at concrete examples, let's discuss a rather common situation described by the following proposition. Suppose that X is a vector space, and Xi is a family of vector subspaces indexed by a poset I. And let's also assume that first of all, for every pair of indices I and j, such that I is less than or equal to j, xi is contained in xj. So they are directed in the same way as our index set is directed. Second, we assume that every xi is equipped with a locally convex topology. Every xi is equipped with a locally convex topology. Such that all the inclusions from xi to xj are continuous. I don't assume that they are topologically injective. They are just injective. So in principle, the topology on x1 induced from x2 can be weaker than the original topology on x1. This is quite typical. We also assume that X is just the union of our family.
Family is not necessarily directed.
Directed because, oh, sorry, thank you very much. No, let's assume that it's directed. Thank you. A directed poset. In this case, I claim that the inductive limit of this family, of this inductive system, is just X equipped with the inductive locally convex topology. Inductive locally convex topology generated by the inclusions maps. Generated by the inclusion maps from xi to x. The proof is actually straightforward, so I leave this as an exercise for you. We simply check the universal property of the inductive limit, which is shown on this picture. So we equip X with the inductive limit topology and inductive locally convex topology and check that it satisfies this universal property. This is more or less straightforward. But this is very useful because in many concrete situations, the inductive limits of locally convex spaces are obtained in exactly this way. Okay, let's now look at concrete examples. Example 1. Well, we consider the following inductive sequence of finite dimensional spaces. So the inclusion maps are just maps of the following simple form. This is the first inclusion. This is the second one. So we simply put 0 to the last slot, and so on. So this is an inductive sequence indexed by natural numbers, and I claim that the inductive limit of this sequence is simply the direct sum of one-dimensional spaces together with the direct sum, the topology of locally convex direct sum, that is, together with the strongest locally convex topology. Strongest locally convex topology. Well, this is an example and an exercise at the same time. This is a rather easy exercise. Well, indeed, the union is the union of the spaces looks like this, and we simply reduce everything to this proposition. Example 2. Example exercise 2. It's just a generalization of example 1, which shows that an arbitrary locally convex direct sum can be interpreted as an inductive limit of finite direct sums. You have an arbitrary family Xi of locally convex spaces, family of locally convex spaces. Then their locally convex direct sum is isomorphic to the inductive limit of finite direct sums xj, where j runs over big J, and big J runs over all finite subsets of I. So for every finite subset of I, we take the respective direct sum. There are obvious inclusions. If J is contained in K, then this direct sum is naturally embedded into the direct sum of over the bigger finite set. And the direct limit is nothing but the direct sum of all the sums. Again, well, the hint is just to reduce everything to this proposition. So all finite direct sums are naturally subspaces of this direct sum, and all the conditions of this proposition are satisfied. Okay, example 3. Which is again a little exercise. If X is an arbitrary topological space, then the space of continuous compactly supported functions on X. So we have already defined a canonical topology on the space some time ago. And I claim that the space is orthomorphic to the inductive limit of the Banach space is CKOX, where the inductive limit is taken over the family of all compact subsets of X. So let's recall that Ck of X denotes the space of those continuous functions on X whose support is contained in K. So clearly, if K1, if we have two compact sets, K1 and K2, such that K1 is contained in K2, then CK1 is contained in CK2. And again, we are in the situation of this proposition.
Why an example 1 we need so strong topology. It seems that the infinity norm is not.
It doesn't work.
Зачем нам не хватит маленьких полномочий?
Try. Try to equip this space with the infinity norm and try to understand why it is this topology is too weak.
All inclusions will be continuous.
All inclusions will be they will be continuous, but it will not satisfy the universal property.
Okay.
They will be continuous. We may equip this with the say L1 norm, the same space,
Yes, yes.
but this doesn't satisfy the universal property. The only space which satisfies the needed property is the space equipped with the strongest locally convex topology. It's an exercise, but I hope it's quite.
Oh, yes,
It's
I
quite-
understand now.
Okay. Example 4. Example 4. Again, we it's similar to example 3, but now we take the space of smooth compactly supported functions. We take an open subset U of Rn, and we choose a compact exhaustion. A compact exhaustion of U. And I claim that the space of smooth, finitely compactly supported functions on U is isomorphic to the inductive limit of the spaces C infinity Kj of U. So let me recall that the space consists of those small functions whose supports are contained in Kj, and it is equipped with the topology induced from C infinity of U. And by the way, well, I'll not write this down explicitly. If in example 3, if x is the second countable, then we can apply a similar trick. We choose a compact exhaustion of x, and we represent the space of continuous compactly supported functions as a countable inductive limit of the respective spaces Ck of j, where now k runs over Kj. Okay. Example 5. Example 5. We take a compact subset of Cn. And we denote by, say, U, script U, an arbitrary base of open neighborhoods of K. And then I claim that the space of holomorphic germs on K, or of K, the space of germs of holomorphic functions on K, is isomorphic to the inductive limit of the spaces of holomorphic functions O of U, where U runs over script U. So U, I must say that U is directed also for the reverse inclusion. You have two open sets, two open neighborhoods of K, and their intersection is also an open neighborhood. So it is directed for the reverse inclusion. And the connected maps in this direct system are just restriction maps. And we can also replace here O of U by the bounded spaces A or quarter of U, which consists of those continuous functions on U, which are homomorphic. Also, of those continuous functions on the quarter of U, which are homomorphic on U. Of course, this is true provided that all sets in script U are bounded. So in this case, the closure view is compact, and we can consider this Banach space. So in all these examples, we see that the direct limits are more or less good topological vector spaces. Normally they are not memorizable, and this is again a rather general picture. A direct limit is often it is not memorizable, but nevertheless they are quite good topological vector spaces. And now example 6 shows that in general the inductive limit of good spaces can be very bad. So let script C0 denote the space of germs of continuous functions. At 0. So we, point on the real line. So we just consider functions defined in neighborhoods of 0, and we identify them in the usual way if they are the same. So two functions are equivalent if they are the same on a smaller neighborhood of 0. So the elements of the space are germs of continuous functions, and similarly to the space of homomorphic germs, it can be equipped, it can be with a natural topology, and it can be topologized in a natural way. So it is the inductive limit of the spaces of continuous functions. We may consider open intervals from -1 over n to 1 over n. Or alternatively, we can consider closed intervals, and the limit will be the same. So this is an inductive limit of a sequence of Banach spaces. What can we say about the topology of this limit? So let's equip C0 with the inductive topology. What can we say about the space? Let's represent it in the following way. C0 is the direct sum of constants. And the subspace of those germs which vanish at 0. Clearly we have such a direct sum decomposition. Exercise. The topology on E induced from C0 is anti-discrete. Which is quite surprising because, well, C0 was the direct limit of Banach spaces. So it's natural to conjecture that the limit, well, it is at least Hausdorff, but it is not Hausdorff. It is very non-Hausdorff because it is a direct sum of a one-dimensional space. Well, the topology on the one-dimensional space is the natural topology, the usual Hausdorff topology. And a very big co-dimensional one subspace whose topology is anti-discrete. So the resulting space is very non-Hausdorff. So this example shows that in general, the direct limit of good spaces can be a very bad space whose topology is not Hausdorff. Probably a natural conjecture here is that maybe the reason why this topology is so bad is that in contrast to the previous examples, in this example, the restriction maps are not injective. If we restrict a continuous function on a big interval to a function onto a smaller interval, it's this map is not injective. But this is not the main reason why this space is so bad, actually, there will be another example in the exercise sheet where the connector maps are injective, but the limit is still very non-Hausdorff. Okay, so that's all for today. At the next lecture, we discuss a special case of inductive limits, the so-called strict inductive limits, which are quite useful and which are more or less well behaved. So in particular, we will see that the strict inductive limit of Hausdorff spaces is Hausdorff, and also it has some other remarkable properties. And then we discuss topologies on spaces of linear operators. There's a rather general way of topologizing the space of linear operators between two locally convex spaces. And then we begin discussing completeness for locally convex spaces. So we introduce complete locally convex spaces. We discuss some examples, and then we discuss completions of locally convex spaces. So in particular, we see that the completion of an arbitrary locally convex spaces, the completion of an arbitrary locally convex space can be conveniently described as a projective limit of Banach spaces. So in particular, if our locally convex space is already complete, we will see that it is isomorphic to projective limit of Banach spaces.